Thanks very much, and for the opportunity to talk. And apologies for not being able to be there in person. So I'm going to talk about work that I've been doing at the University of Southampton in the UK and also Princeton Climate Institute in collaboration with colleagues from the University of Montana, and also support from and collaboration from UNESCO IHP for many years now, on work around early warning, focused on flood and droughts, and the use of AI, and particularly machine learning, that we've been using to enhance this capability. So there are many challenges in trying to do this, in terms of monitoring and forecasting and translating that information into useful early warning information that can really help kind of decision making. And some of these have been mentioned before, so I'll quickly go through those. So one of the biggest challenges is kind of ungauged regions, data scarce regions, where there's often arguably the greatest need for this kind of information, but there is lack of data on the ground. So we're often reliant on satellites to provide information. That's often not direct measurements of the variables that we're interested in, or we have to rely on models as well. And those can be uncertain. And again, that's a reflection of data scarcity. Resolution and timeliness is really important, especially thinking about kind of local needs and trying to resolve the local variability in hydrology and hazards, and also the kind of sectors and activities that are happening, that are often very small scale as well. Thinking about smallholder farming systems or urban environments. Information should be consistent and timely. We often struggle with that. So providing information from hours to days for flooding, or days to weeks or even more for drought. And the skill of those forecasts is really important. We want those to be as skillful as possible and also robust and reliable. That's very data dependent for things like flood forecasting, and also highly dependent on the skill of rainfall forecasts, let alone what happens when that gets translated into floods on the ground. The same for drought forecasts. We're trying to provide information at subnational, certainly, ideally down to the river basin or even locally, and across many scales. So not just the next week or seasonally, but that intra-seasonal timescale is important. We can do that using models, climate models and hydrological models, but the skill is very model dependent and location dependent, and the skill is often limited to the first few weeks of the forecast. And another aspect is what we do with that information. So we can produce information, but how do we disseminate it? And the challenge here is that we have many different types of users that need this in different formats and tailored to their needs. And often users have low technical capacity and cannot engage with these complex systems. So we need to provide information in readily accessible formats and methods. And I wanted to reiterate this idea of providing information at the local scale. That's really important because we have a lot of landscape variability. A lot of this is driven by rainfall and especially in areas where it's intermittent and very focused, maybe highly convective systems. And this leads to a lot of variability in things like soil moisture, drought, runoff generation, and flooding. And it's also driven by the landscape features, in terms of topography and land use, vegetation, and soils, and the underlying geology as well for the interactions with groundwater. Some examples on the left here, just showing some soil moisture that we generated from models combined with satellites at very high resolution. Just showing, even if you look at a very large scale, you can see a lot of complexity at the top there. Once you start to zoom in, again, you see this complexity, high spatial variability in soil moisture across these relatively small domains that we would like to capture, because we know that they produce different extremes on the flood and the drought side of things. And you think about the actual application and end users, as I mentioned before, it's really important to provide local information in complex urban areas or in smallholder farming systems, for example, on the right there. Very small fields, not very regular. When you compare this with, say, the US, where you have industrialized farming, it's much easier in those contexts to provide information from traditional methods, so that's models or satellites at coarser resolution. So I'll give a few examples of the work we've been doing to try to address some of these issues and basically leverage the power of AI and machine learning. One is in downscaling precipitation to finer scale. So often we are reliant on satellite or model products or gridded gauge products to provide precipitation inputs to our application. So modeling, for example, it's often too coarse to replicate those the intermittent and small scale features of precipitation in many regions of the world. So machine learning can basically integrate a number of predictors to help us downscale those data sets. So just on the left is an example of the methods we've been using over the years to basically take coarse precipitation and use higher resolution landscape covariates and also other dynamic information to downscale to the order of, say, kilometers, which gets to the more of the representative scale of actual precipitation. Here's some example results of that methodology. This is a paper, this is actually from 10 years ago. So this kind of just shows that machine learning techniques have been around for a very long time, actually, in the spectrum of different data-driven methods. On the left is the observational product showing the fine scale features of convective precipitation, and across the top is some upscale versions, which is kind of typical of what we might get from these gridded data sets that we might use normally. And then down the bottom, in the middle and the bottom rows, we can see some machine learning estimates that give us that can actually replicate those fine scale features. And some error assessments on the right just shows that these methods can actually get quite close to replicating the more extreme values that we are very interested in terms of, say, flooding. Another example is predicting hydrology, and particularly soil moisture at fine scales, using modeling, but enhanced by machine learning methods. And this is really important because we would like to predict at the field scale, so that's tens of meters. That's impossible using modeling over large areas. So the computational and data limitations are really restrictive here. So we developed a technique that basically clusters the landscape using landscape features at high resolution, so tens of meters in terms of soil properties or topography or vegetation land cover, to develop what we call hydrological response units that we think behave the same way hydrologically, and these become the computational units of the model. The model then runs on that HRU scale, and the outputs are then disaggregated back to the tens of meters of scale using that basically backward clustering. And the way we do that is shown on the right. And then we can get what we call hyper-resolution soil moisture and other kind of drought and flood indices. We've been applying this and testing this a few years ago in a paper focused on Zambia, where the ultimate goal was predicting crop yield at very high resolution. And the examples here on the left show mean root zone soil moisture for April in the region. And you can see the complexity of the model results. And this is also constrained by satellite remote sensing as well. And as you zoom in, you can see very complex spatial patterns that we've actually tested over dense in situ soil moisture probe networks to show that it's actually picking up that variability in a realistic way. On the right is mean soil temperature as well as another example of the model output. We were then applying that in another machine learning application to predict crop yields a few months in advance. And we can see the explanation of that model in terms of what the most important predictors were. And it turns out the soil moisture in April was one of the most important predictors for crop yields versus what is traditionally used, which is often vegetation indices, which has much less power in providing those predictions. The third example is flood inundation monitoring and forecasting that we've been implementing in our operational system. So generally, this is done from modeling or satellite information for monitoring flood inundation. Machine learning can complement this by providing kind of landscape informed estimates and also forecasts as well. So our approach has been taking microwave sensor retrievals of fractional water inundation. And the microwave approach, of course, allows us to see through clouds, so we can do this on a more regular basis. But the trade-off is that those retrievals are quite coarse. In the case of SMAP, we're using the 36-kilometer product, which is not actually that useful. What we do with the machine learning is combine that with optical infrared information on classification of land cover, dynamic classification at the tens of meters. So that connection between the large scale view and the local scale view is very powerful. Here's an example of how we've used that to look at, for example, Cyclone Idai back in 2019, which impacted heavily across Mozambique and Zimbabwe and other places in the southeast of Africa. So this is back in 2019. You can see the detail that we're producing in the monitoring of that flood inundation as a result from the cyclone. And as I said, we're also doing forecasts as well. So that's actually taking the rainfall forecast that we use for the hydrological forecasting and including other predictor information from topography, soils, and vegetation that's giving us the spatial variability in that inundation. An example on the right just shows some examples of forecasts out to 1 day, 3 day, and 10 days, and a comparison with an independent satellite estimate of the monitoring from the ARIA sensor. So we've been trying to take all these different techniques that are looking at different aspects of the kind of early warning modeling chain and putting it all together in operational systems. This is a system that we've been running for about a year now, operationally in a kind of a pilot phase, focused on the Buzi-Pungwe Save basins of Zimbabwe, Mozambique, again, the area that was affected by Cyclone Idai and other cyclones over the last few years. The system is updated every day for monitoring at 30-meter resolution. So that's rainfall, hydrology, derived flood and drought indices, and there's also a short-term forecast out to 10 days that's giving us those variables and indices as well. And we have some recent pilot work where we're trying to go that step further and actually translate this quite complex information into something that can be used by a wide variety of end users. So this is using an AI-assisted SMS or WhatsApp workflow. So basically, the user will put in an SMS request, and this could be just natural language, a generic kind of request. What is the flooding going to be over the next few days for this particular basin? We use a large language model to process that request and pull out parameters about the variable, the time scale, and the location. That gets geocoded, extracts the data, and then we send an SMS or WhatsApp response back to the user. So this is working quite well in actually translating quite complex information into something the user can interact with quite easily. This is the last slide, in terms of ongoing challenges and ways forward, a lot of this has been covered by many people over the last couple of sessions. Again, there's a lot of dependency on data, so diverse data collection, continued diverse data collection is imperative. Understanding the sampling sensitivity in these machine learning models and how skillful they are needs to be understood. There's also a question about transferability, especially where we have data scarcity. We may train models in somewhere else and then try to transfer it. So understanding how we can do that is really important. And just to reiterate, the kind of interpretation and process understanding is really important, so we can have a bit of understanding of what is driving these predictions and the sensitivity of those as well. And this all feeds into that question of trust and transparency in these methods, especially in how we use these in operational contexts. I mean, it's bad enough trying for users to understand the kind of workflow with models and satellite remote sensing. Once we start to add in machine learning, essentially black boxes in some sense, then it becomes a real challenge. I just want to finally just finish on the figure on the right, which is actually an AI generated image of the use of AI and machine learning and drought forecasting. And at first glance, it looks quite reasonable. When you start looking at the details, it's quite puzzling and a little bit strange in some ways. So it's kind of a simple reflection of some of the challenges that we still face in trusting AI to actually make useful information and forecasts that we can use for early warning systems. So I'll finish there. Thanks very much.